talk will be given by Reuben, and it's going to be, as it says, on the complexity landscape of checking progress in proofs. In circular proofs.
Oh, okay. Okay, so I'm Reuben Rowe, also from Royal Holloway, and this is joint work with my colleagues Liron and her student in Israel, and my colleague Andrei in Sheffield. So we are looking at the infinite descent property, which is central to checking the validity of derivations in cyclic proof theory, and is also a core aspect of the size change approach to checking program termination. So there exist a couple of algorithms in the literature already coming out of these applications for deciding infinite descent. And what we do in our paper is we propose two new algorithms. We carry out comparative parameterized analysis of the time complexity of these algorithms. And we also implement and experimentally evaluate them within the cyclist theorem prover. So to give you a bit of intuition about what infinite descent is, I'll talk about it in the context of an example from cyclic proof. So cyclic proofs are artifacts of really the proof theoretic formalization of the logical principle of reasoning by infinite descent. So we could consider, for example, Euclid's infinite descent proof of the irrationality of the square root of 2. So here I have an example derivation, and the statement that it derives at the bottom is expressing that it's not the case that the square root of 2 is rational. And that's expressed as there existing two natural numbers x0 and x1, such that the square of x0 is 2 times the square of x2. Over here on the left, I've abstracted some straightforward arithmetic reasoning, which allows us to then infer that, in fact, x1 is strictly less than x0, and that, moreover, there exists another natural number x2, with the relationship that the square of x2 is half the square of x1. I can then apply some analogous reasoning, which I've abstracted over here, to further derive that there's a further natural number x3, and so on and so forth. And formally, we represent this as an infinitely deep derivation. And in order to justify that the statement that it derives at the root is a valid logical inference, we can do a proof by contradiction. So assuming for contradiction that it's not valid, this would then entail that there is an infinite sequence of natural numbers represented by variables that we can trace through an infinite path in this proof, such that at various points in this proof, infinitely many points, in fact, there is a strict decrease with these numbers. So this would entail an infinitely descending chain of natural numbers, which is the contradiction. When such infinite reasoning is regular, we can represent it as a finite derivation with cycles. And so the infinite descent property here is really the core thing that allows us to justify the logical statements that we derive with these cyclic proofs. So over the last couple of decades, this cyclic proof treatment has been applied in many different contexts very successfully, since it's a general and flexible technique for applying inductive reasoning implicitly, by which I mean you don't have to come up with inductive invariants up front. But what all of the different cyclic proof systems, or at least most of them that we find in the literature, have in common is that they're all different instantiations of the same basic abstract framework. So when we're considering infinite descent in general in cyclic proof systems, of course, we're not interested in the specific logical statements. What we're really interested in is the underlying structure of the proof derivations. So we abstract these simply as graphs. The logical statements get abstracted as vertices, which have edges representing So we have edges from vertices representing conclusions of inference rules to vertices representing the premises. We also have to capture this notion of being able to trace elements through the logical statements in the proof, and we do this by associating a collection of abstract entities that we call positions with the vertices. And the other piece of information we need is to know how we can track these, the relationship between these positions through the paths in the proof. And so for that we use things which we call sloped relations, and these say whether consecutive positions, whether they're in a non-increasing relationship, which we represent with this horizontally sloped arrow, or whether they're in a progressing or decreasing relationship, which we represent with this downward diagonally sloped arrow. So this can also capture naturally the size change termination context. We can think of the graph structures representing the call graph of a program, the positions as representing the parameters of the functions which are called, and then our sloped relations correspond to what are called size change graphs in the literature. So we've called these relations sloped relations, and for that reason we call these abstract graphs sloped graphs. And then in this setting, the infinite descent property is expressed through the statement that for every infinite path in this sloped graph, we can trace a sequence of positions that progresses infinitely often, and where progression is given, of course, by two consecutive positions being related by one of these downward slopes. So I've mentioned that there are a couple of algorithms already in the literature for deciding the infinite descent condition. One of them is automata theoretic and checks inclusion between omega automata. The other is relation-based and relies on Ramsey theoretic principles. It's known already that the infinite descent property is PSPACE-complete, so unsurprisingly, the time complexity of these two algorithms are exponential in the size of the underlying sloped graph. What I'll do now is I'll give a quick overview of these existing algorithms, then I'll talk about the new algorithms that we've given in the paper. The automaton-based algorithm constructs two Buki automata which recognize infinite sequences consisting of vertices in the underlying sloped graph. So we have an automaton that we call a path automaton, and this recognizes all infinite paths in the graph. We have another automaton called the trace automaton, and this recognizes all such infinite paths that have an infinitely progressing trace of positions. And then checking the infinite descent property amounts to checking an inclusion of the path automaton within the trace automaton, which of course is equivalent to checking emptiness of the intersection of the path automaton and the complement of the trace automaton. So it's this complementation operation which leads to the exponential complexity of checking the infinite descent with this method. And in this context, for this construction, the trace automaton, the size of the trace automaton is dependent on both the number of vertices in the underlying graph and also this quantity which we call the vertex width, which is the maximum number of these positions which occur in any given vertex of the graph. And so because the trace automaton depends on both, then the exponential component of checking this inclusion also depends on both of these parameters, as well as having some polynomial dependence on it as well. In contrast, the relation-based algorithm works by computing a set of sloped relations for each pair of vertices, and each of these sloped relations corresponds to the composition of all of the relations along some finite path between those two vertices. This can straightforwardly be described inductively, where we start out with singleton sets containing sloped relations which we obtain from the underlying graph, and then we saturate them by composing the sloped relations in each of these sets. And with this method to check infinite descent, what we have to do is we have to check that for each relation corresponding to a path from a vertex to itself, it has a loop with one of these decreasing slopes in it. So this can be seen as an instance of the algebraic path problem, and so we can use the generalization of the Floyd-Warshall all points shortest path algorithm for it. So this is straightforwardly seen to be polynomial, in fact, cubic in the number of vertices of the graph. Interestingly, it is only exponential in this one parameter, the vertex width. So there's a separation in the complexity between the two parameters. This algorithm also has some nice properties, which is that it allows early termination when the underlying sloped graph doesn't in fact satisfy infinite descent. And it also allows practical optimization, which doesn't in fact change the overall complexity, but makes a difference in practice, which allows us to lift an ordering on the slopes to become a partial relation on the sloped relations. And so we can get away with only considering sloped relations which are minimal with respect to this partial order. A question is raised, can we come up with an automaton-based approach which mirrors this separation in the complexity between the two different parameters? And the answer is that we can, and we can do this by changing from constructing automata that recognize vertices in the graph to recognizing instead sloped relations. So we have the same scheme. We have a path automaton which recognizes sequences of these sloped relations that do correspond to actual infinite paths in the underlying graph. But now the trace automaton, it recognizes sequences of sloped relations that simply admit some decreasing trace and aren't necessarily connected with the underlying structure of the graph. So this means that the trace automaton now only depends, in fact, linearly just on the vertex width. And so the exponential component in checking the inclusion in this scheme also only depends on the vertex width. And what we see is that we've traded off exponential complexity in the number of vertices for a bit of extra polynomial complexity there. We can also improve the relation-based approach by taking advantage of some symmetries inherent in the problem. So in fact, we don't need to consider all paths between vertices. So for example, if we have edges between two vertices, V1 and V2, if we check the alternating path between them that starts from vertex V1, well, this will have a descending trace if and only if the infinite path, alternating path starting from V2 has a descending trace. So we can modify the Floyd-Warshall-Kleene algorithm to avoid considering unnecessary paths by fixing an arbitrary order on the vertices. And this means that when we're computing the sets of sloped relations, we only need to consider paths between particular vertices that pass through intermediate vertices which are less than or equal to the smaller of the endpoints according to this order. So for this reason, we call this modification of Floyd-Warshall-Kleene the order-reduced algorithm. And what we see in the complexity analysis is that it actually saves an exponential factor in the vertex width compared with the original Floyd-Warshall-Kleene. What we see is that we have quite a complex landscape in terms of different algorithms that exist, and the relationship that they have with each other really depends on how the values of these two different parameters compare with one another. So in order to evaluate how these algorithms perform in practice, we implemented them in C++ and integrated them within the cyclist theorem prover. And we tested it on a selection of test cases which were present in the cyclist framework already, and we also handcrafted some examples which were designed to elicit the worst case behavior of these algorithms, which fix one particular of the parameters and then vary the other, and testing on both positive and negative examples. So what we found is that for the so-called real-world examples, we found a clear improvement with the relation-based methods over the automata-based methods. So the relation-based methods are shown here in the yellow and red lines. We also saw, in line with the complexity analysis, that the order-reduced algorithm performed slightly better than the Floyd-Warshall-Kleene algorithm, although kind of in these real-world examples there was not so much in it. So testing it on the worst case benchmarks, we sort of see improvements of the order-reduced algorithms over the standard Floyd-Warshall-Kleene, which was mirrored in both positive and negative examples, but the performance of the automata-based methods really depended on whether we were testing positive or negative examples. And then lastly, on the examples that vary the vertex width, here we saw that the relation-based methods were clear winners. So just to sum up, we studied infinite descent in an abstract logic-independent setting. We proposed 2 new algorithms for deciding the infinite descent property. We analyzed the complexity trade-offs which were inherent in the different algorithms and experimentally evaluated them as well. Thank you.
Questions?
Thanks for the talk. With the order reduced method, did you notice any practical difference with the ordering chosen? Did you just generate it at random, or?
Yeah, that's a really interesting question. So, in fact, it does make a difference what ordering you choose. We just, in our experiments, we just took a sort of natural ordering in the definition of the graphs. But what you want to do is you want to order the vertices which are sort of hubs. You want to put them last in the order, because then you can discount more paths. But we did some experiments, which we haven't reported in the paper, with different orderings. But sort of what we found, at least in the real-world examples, is because the values for the parameters are quite small there, the overhead of actually reordering the vertices kind of took over the running time of the algorithms. Yeah.
Okay, thanks.
So I would have imagined that the graphs that you have from proofs have much more structure than being arbitrary graphs or even captured by small w. So are you sure that this is PSPACE-complete even for the class of proofs that you get?
Yeah, I mean, this is also a very interesting question. I don't really have an exact answer about what are the structures that we see in practice in proofs. I can say that we noticed that the vertex width of proofs in the wild, it's sort of comparable to the number of vertices. I mean, so we can do a procedure that minimizes the number of vertices while kind of keeping the topology the same. And once we do this, we kind of see that we get similar vertex width to the number of vertices. But we saw vertex widths going up to maybe 12 in some cases. So I don't think it's really the case that in proofs in the wild the vertex width is always very small. Sometimes it can be large. But I don't have.
There's nothing like it's not bounded tree width or other kinds of measures of graphs.
I mean, I think you could. You could maybe do something like trying to bound the tree width as you're doing some proof search, to restrict the proofs that you actually find. I'm not sure if a priori there's some kind of restriction. No.
Okay, thanks.
Thank you very much.
All right. Thank you.